Tonight, we're going to talk about the most successful theory ever created by human beings. It predicts the behavior of the smallest building blocks of reality with a precision that borders on absurd. We're talking about accuracy to 11 decimal places. That's like predicting the distance from New York to Los Angeles and being off by less than the width of a single atom. The standard model of particle physics has passed every test we've thrown at it for over 50 years. And yet, physicists know it's wrong, not slightly off, fundamentally incomplete. There are cracks forming in the foundation, strange results from experiments that shouldn't exist if the standard model were the final answer. And what's hiding in those cracks might be the biggest revolution in physics since Einstein. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, make yourself comfortable. Let's begin. Let's start with a question that sounds almost ridiculous. What is everything made of? Not in a philosophical sense. In a literal physical, you can measure it in a laboratory sense. What are the fundamental ingredients of reality? If you take any object, your hand, this screen, the air you're breathing, and you zoom in far enough, past the molecules, past the atoms, past the protons and neutrons, what do you find at the very bottom? What are the smallest, most basic building blocks of the universe? This question haunted physicists for centuries. The ancient Greeks thought everything is made of 4 elements: earth, water, air, and fire. It was a nice idea, elegant even, but it was completely wrong. In the 1800s, chemists discovered the periodic table. They found that matter was made of atoms, and there were different types of atoms corresponding to different elements: hydrogen, oxygen, carbon, iron, gold. About 90 naturally occurring elements in total. That was better, but it still wasn't the bottom. Atoms turned out to have structure. They had a nucleus made of protons and neutrons, surrounded by a cloud of electrons. And then, in the mid-20th century, physicists discovered that protons and neutrons weren't fundamental either. They were made of even smaller particles called quarks. Eventually, after decades of theoretical breakthroughs and experimental discoveries, physicists assembled what is arguably the single greatest intellectual achievement of our species. A theory that describes the fundamental building blocks of reality and the rules governing how they interact. They called it the standard model of particle physics. The standard model is not what most people imagine when they hear the phrase. It's not a vague philosophical framework. It's not a rough sketch or an approximation. It's a precise mathematical structure that makes predictions about the behavior of subatomic particles with an accuracy that borders on the absurd. It's been tested thousands of times in experiments conducted all over the world, and it has passed virtually every test. When physicists calculate something using the standard model and then go measure it in a laboratory, the numbers match. Not roughly, not approximately. They match to an extraordinary number of decimal places. But to understand why this theory matters, and more importantly, why its cracks are so significant, you first need to understand what it actually says. So let's build it from the ground up. Everything in the universe, every star, every planet, every grain of sand, every cell in your body, every thought in your brain is made of a small number of fundamental particles. When I say fundamental, I mean these particles have no internal structure. They're not made of anything smaller as far as we can tell. They are the bottom of the ladder, the place where you can't zoom in any further. The Standard Model organizes these fundamental particles into two main families. The first family is called fermions. Fermions are the matter particles. They're what stuff is made of. The second family is called bosons. Bosons are the force carriers. They're the particles that transmit the forces between matter particles. Think of it this way. Fermions are the bricks. Bosons are the mortar that holds the bricks together and governs how they interact. Let's start with the fermions, the matter particles. There are 12 of them in total, and they come in two types, 6 quarks and 6 leptons. Quarks are the particles that make up protons and neutrons, which in turn make up the nuclei of atoms. There are 6 types of quarks, and physicists gave them whimsical names: up, down, charm, strange, top, and bottom. These names don't mean anything intuitive, they're just labels. But the properties of these quarks are profoundly important. The up quark and the down quark are the lightest and most stable. They're the ones that make up ordinary matter. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. That's it. Every proton and neutron in every atom in your body and in every star in the universe is built from just these 2 types of quarks. The other 4 quarks, charm, strange, top and bottom, are heavier and unstable. They exist only fleetingly in high-energy environments like particle collisions or the conditions just after the Big Bang. They decay almost instantly into lighter particles, but they're real. We've detected all of them in experiments over the past several decades. Strange particles were first observed in the 1950s in cosmic ray experiments, and when the quark model was proposed in 1964, the strange quark was introduced to explain them. The charm quark was discovered in 1974 at both Stanford and Brookhaven National Laboratory simultaneously, an event so surprising it's called the November Revolution in Particle Physics. The bottom quark was found in 1977 at Fermilab, and the top quark, the last to be discovered, was finally detected in 1995, also at Fermilab near Chicago. The top quark is the heaviest of all known fundamental particles. A single top quark has a mass roughly the same as an entire atom of tungsten, which is remarkable for something that's supposed to be a fundamental building block. It's so heavy that it decays before it can even form a bound state with other quarks, something that makes it unique among all the quarks. Now, the leptons. There are also 6 of these. The most familiar lepton is the electron. You know, electrons? They orbit atomic nuclei. They flow through wires as electrical current. They're responsible for chemistry, for the bonds between atoms, for essentially all of the material properties you experience in daily life. The hardness of steel, the wetness of water, the color of a sunset. All of that comes down to how electrons behave. The electron has 2 heavier cousins, the muon and the tau. These are essentially identical to the electron in every way except mass. The muon is about 207 times heavier than the electron. The tau is about 3,490 times heavier. Like the heavier quarks, the muon and the tau are unstable. They decay quickly into lighter particles. But while they exist, they behave exactly like electrons. They have the same electric charge. They interact through the same forces. They're just heavier. And nobody knows why nature decided to make 3 copies of essentially the same particle at different masses. That's one of the puzzles of the standard model, but we'll get to that later. Each of these charged leptons has a partner called a neutrino. The electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are amongst the strangest particles in nature. They have almost no mass, they carry no electric charge, they interact with other matter so weakly that they can pass through the entire Earth without disturbing a single atom. Right now, as you listen to this, about 65 billion neutrinos from the Sun are passing through every square centimeter of your body every single second. You don't feel them. You can't detect them without enormous, specialized equipment. They're like ghosts drifting through the material world, almost completely invisible. To detect neutrinos, scientists have built massive underground detectors. Tanks filled with tens of thousands of tons of ultra-pure water, or liquid scintillator, buried deep beneath mountains to shield them from other particles. Even with these enormous detectors, they catch only a handful of neutrinos out of the trillions that pass through every second. That's how weakly neutrinos interact with matter. They are the universe's ultimate introverts. So that's 12 matter particles, 6 quarks and 6 leptons arranged in 3 generations. The first generation contains the lightest particles, the up quark, the down quark, the electron, and the electron neutrino. These are the particles that make up all ordinary stable matter. Everything you see around you is built from first generation particles. The second generation contains heavier versions, the charm quark, the strange quark, the muon, and the muon neutrino. The third generation is heavier still. The top quark, the bottom quark, the tau, and the tau neutrino. The second and third generations are unstable. They decay into first generation particles almost immediately after being created. But they exist. They're part of the recipe. Now, having the ingredients isn't enough. You also need to know how they interact, what forces act between them, how they push and pull on each other. This is where the bosons come in. The standard model describes 3 of the 4 known fundamental forces of nature: the electromagnetic force, the strong nuclear force, and the weak nuclear force. Each force is carried by its own set of boson particles. The electromagnetic force is the one you're most familiar with, even if you don't realize it. It's responsible for light, for radio waves, for the attraction between positive and negative charges, for magnets sticking to your refrigerator. At the quantum level, the electromagnetic force is carried by a particle called the photon. When 2 electrons repel each other, what's actually happening is that they're exchanging photons between them. The photon is massless, which is why the electromagnetic force has infinite range. It can reach across the entire universe. The light from a star billions of light years away reaches your eye because photons have no mass and can travel forever at the speed of light. The strong nuclear force is the most powerful force in nature, but it operates only at incredibly short distances, roughly the size of an atomic nucleus. Its job is to hold quarks together inside protons and neutrons, and to hold protons and neutrons together inside atomic nuclei. Without the strong force, atomic nuclei would fly apart. Protons are positively charged, and like charges repel. The electromagnetic force is constantly trying to push protons away from each other inside every nucleus. The strong force overcomes this repulsion, binding the nucleus together. The strong force is carried by particles called gluons. There are 8 types of gluons, and they interact not just with quarks, but also with each other, which makes the strong force extraordinarily complex. This self-interaction of gluons is what gives the strong force some of its most unusual properties, including something called confinement. You can never isolate a single quark. If you try to pull a quark out of a proton, the energy you put in actually creates new quarks. It's as if nature refuses to let quarks exist alone. The weak nuclear force is responsible for certain types of radioactive decay. It's the force that allows a neutron to transform into a proton, emitting an electron and a neutrino in the process. This is what happens in beta decay, a type of radioactivity. The weak force is also crucial for the nuclear reactions that power the sun. Without the weak force, the sun couldn't fuse hydrogen into helium, and life on Earth wouldn't exist. The weak force is carried by 3 particles: the W+ boson, the W- boson, and the Z boson. Unlike the photon, these bosons are massive. The W bosons have a mass about 86 times that of a proton, and the Z boson is even heavier at about 97 times the proton mass. Because these force carriers are so heavy, the weak force has a very short range. It operates only at distances smaller than the diameter of a proton. This is why radioactive decay can happen inside atomic nuclei but doesn't affect objects at larger scales. And then there's the Higgs boson. The Higgs boson is different from the other bosons because it's not a force carrier in the traditional sense. Instead, it's associated with the Higgs field, an invisible field that permeates all of space. The Higgs field is the mechanism that gives particles their mass. Without it, every particle in the universe would be massless, traveling at the speed of light. There would be no atoms, no chemistry, no stars, no planets, no life. Nothing would hold together. Think of the Higgs field like this. Imagine walking through a room that's packed with people. If you're someone nobody recognizes, you can walk straight through without anyone stopping you. That's like a massless particle moving through the Higgs field. It doesn't interact, but if you're someone famous, people crowd around you, slow you down, make it harder for you to move. That's what the Higgs field does to particles with mass. It creates a kind of resistance, a drag, that manifests as what we experience as mass. Different particles interact with the Higgs field to different degrees, which is why different particles have different masses. The Higgs boson was predicted in 1964 independently by several physicists, including Peter Higgs and Francois Englert. But it wasn't discovered until 2012 at the Large Hadron Collider at CERN in Switzerland. The discovery was a monumental achievement. It took nearly 50 years of searching. The construction of the largest and most complex machine ever built by humanity. A circular tunnel, 27 kilometers in circumference, buried beneath the Swiss-French border, and the collaboration of thousands of scientists from over 100 countries. When the discovery was announced on the 4th of July, 2012, Peter Higgs, then 83 years old, was in the audience. He wept. It confirmed the final piece of the Standard Model's particle zoo. Every particle the theory predicted had now been found. The Standard Model was complete. And that completeness is backed by extraordinary precision. Let me give you an example that shows just how precise this theory really is. One of the most precisely measured quantities in all of physics is something called the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet, spinning on its axis. The strength of this tiny magnet can be calculated using the standard model, and it can be measured in the laboratory. When you compare the two numbers, the theoretical prediction and the experimental measurement, they agree to better than 10 parts per billion. That's an accuracy of about 11 significant digits. Let me put that in perspective. Imagine you wanted to predict the distance from London to Sydney, which is about 10,550 miles. If your prediction were as accurate as the standard model's prediction of the electron's magnetic moment, you'd be off by less than the width of a human hair. You'd predict a distance of thousands of miles and get it right to within a fraction of a millimeter. That's not just good. That's the most precise agreement between theory and experiment in the history of science. No other theory in any branch of science comes close to this level of accuracy. Not biology, not chemistry, not even other areas of physics. The standard model's prediction of the electron's anomalous magnetic moment is the gold standard for what a scientific theory can achieve. And it's not just one measurement. The standard model makes thousands of predictions about particle interactions. How often certain decays happen, what angles particles scatter at, what energies are produced in collisions, the masses and lifetimes of particles, and in test after test, experiment after experiment, the predictions match reality. The Large Hadron Collider at CERN, the largest and most powerful particle accelerator ever built, smashes protons together at nearly the speed of light. The energy of these collisions briefly recreates conditions that existed less than a trillionth of a second after the Big Bang. In these collisions, all sorts of particles are created. Quarks, gluons, W and Z bosons, Higgs bosons, top quarks. The standard model predicts exactly how often each type of particle should be produced, how it should decay, and what the resulting particles should look like in the detectors. And the predictions match, over and over again, with astonishing consistency. Think about how remarkable this is. Humans, living on a small planet orbiting an ordinary star, have figured out the fundamental building blocks of reality and written down equations that predict their behavior with extraordinary accuracy. We can't see these particles. They're far too small to see, even with the most powerful microscopes. A quark is at least 10,000 times smaller than a proton, which is itself 100,000 times smaller than an atom, which is itself millions of times smaller than anything you can see with your naked eye. And yet, we know they're there. We know what they do. We know how they interact. And we can predict their behavior to 11 decimal places. The standard model represents something profound about human capability. It says that the universe, at its most fundamental level, is comprehensible. That reality has rules. That those rules can be discovered by careful observation, creative thinking, and rigorous mathematics. It's the closest thing we have to a complete instruction manual for the universe at the smallest scales. Now, you might be thinking, if this theory is so spectacularly successful, if it predicts reality with unmatched precision, if every particle it predicted has been found, then what's the problem? Why do physicists believe it's incomplete? Why would anyone doubt a theory that works this well? This is where the story gets fascinating, because the standard model doesn't just have small problems. It has enormous gaping holes that it cannot address at all. And it has subtle cracks, tiny discrepancies between what it predicts and what experiments actually measure. Discrepancies that refuse to go away no matter how many times they're checked. Let's start with the most obvious omission. The standard model describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. But it says nothing about the 4th force, gravity, the force that keeps your feet on the ground, the force that holds planets in orbit, the force that governs the large-scale structure of the entire universe. The standard model simply doesn't include gravity. It pretends gravity doesn't exist. Now, for particle physics, this mostly doesn't matter. Gravity is extraordinarily weak compared to the other forces. The electromagnetic force between 2 electrons is roughly 10 to the 42 times stronger than the gravitational force between them. That's a 1 followed by 42 zeros. At the scale of subatomic particles, gravity is so feeble that it's completely negligible. Particles don't care about gravity. They're governed by the other 3 forces, but gravity obviously exists. It shapes the cosmos. It forms stars and galaxies. It bends space and time. It creates black holes. And we have a brilliant theory of gravity already. Einstein's general theory of relativity, published in 1915, describes gravity not as a force in the traditional sense, but as a curvature of space-time caused by mass and energy. General relativity works spectacularly well for large-scale phenomena. It predicts the orbits of planets, the bending of light around massive objects, the expansion of the universe, and the existence of gravitational waves, all of which have been confirmed by observation. The problem is that general relativity and the standard model are fundamentally incompatible. They use different mathematical frameworks. They make different assumptions about the nature of space and time. They work beautifully in their own domains. The standard model for the very small, general relativity for the very large. But when you try to combine them, when you try to describe situations where both quantum mechanics and gravity matter simultaneously, the mathematics breaks down. You get infinities, nonsensical answers. The equations literally produce results that are meaningless. Where does this matter? In the centers of black holes, where enormous mass is compressed into an incredibly small space. At the moment of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom. In these extreme environments, you need both quantum mechanics and gravity to describe what's happening. And our theories can't do it. The standard model and general relativity each work perfectly in their own territory, but they can't talk to each other. It's as if we have 2 different instruction manuals for the universe, one for the quantum world and one for the gravitational world, and they're written in different languages that are fundamentally incompatible. This isn't a minor issue, it's a deep, structural problem. A truly complete theory of physics would need to describe all 4 forces in a single, unified framework. The standard model can't do that. It's missing one of the most important forces in nature. And there are other issues. The standard model has about 19 free parameters. These are numbers like the masses of the particles, the strengths of the forces, and various mixing angles that the theory doesn't predict. They have to be measured in experiments and then plugged into the equations by hand. The standard model can tell you how particles with these masses and charges will behave, but it can't tell you why those particular masses and charges exist in the first place. Why does the electron have the mass it has? Why is the strong force as strong as it is? Why are there 3 generations of matter particles, and not 2 or 4 or 17? The standard model doesn't answer any of these questions. It just says, these are the numbers we measured. Plug them in and the theory works. This is deeply unsatisfying to physicists. A truly fundamental theory shouldn't have this many adjustable knobs. It should explain why the numbers are what they are, not just accept them as given inputs. The fact that the standard model needs 19 free parameters suggests that there's a deeper theory underneath, one that would explain where these numbers come from. There's also the question of elegance, or rather, the lack of it. The standard model works, but it's not particularly beautiful as a mathematical structure. It's a patchwork. 3 different forces described by 3 different mathematical frameworks, stitched together into a single theory that functions but doesn't have the kind of deep underlying unity that physicists expect from a truly fundamental theory. It's as if someone built a car by welding together parts from 3 different vehicles. It drives, but it doesn't look like it was designed as a single coherent machine. Physicists have a long history of discovering that seemingly different phenomena are actually manifestations of the same underlying physics. In the 1860s, James Clerk Maxwell showed that electricity and magnetism were 2 aspects of a single electromagnetic force. In the 1960s and 70s, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak nuclear force could be unified into a single electroweak force at high energies. This pattern of unification suggests that perhaps all the forces, including gravity, are different facets of a single underlying force that split apart as the universe cooled after the Big Bang. But the standard model, despite unifying 2 of the forces, has not achieved full unification. It still has 3 separate pieces. And integrating gravity into the framework remains one of the deepest unsolved problems in all of physics. So here's where we stand. The standard model is the most successful predictive theory ever created. It describes the fundamental particles and 3 of the 4 fundamental forces with extraordinary precision. Every particle it predicted has been found. Its calculations match experimental results to an almost absurd degree of accuracy. By any reasonable standard, it's a triumph of human intellect. But it's also incomplete. It can't include gravity. It can't explain why its own parameters have the values they do. It has the feel of a provisional theory, an approximation that captures the behavior of nature at the energies we can currently probe, but misses something deeper. And that brings us to the cracks. Because beyond these theoretical dissatisfactions, there are actual experimental results that don't quite match what the standard model predicts. Not dramatic failures, not wildly wrong answers, just subtle deviations. Persistent whispers from nature suggesting that there's something the standard model isn't accounting for. These whispers are small, often at the very edge of statistical significance. Any single one of them could be a measurement error, a statistical fluke, a miscalculation, but there are several of them. They come from different experiments measuring different things, and they all point in the same direction, towards something new, something the standard model can't explain. The standard model is like a map that's almost perfect. It shows you every road, every building, every river with incredible accuracy. But there are a few places where the map and the territory don't quite match. A road that the map says should go straight, but actually curves slightly. A building that the map says should be here, but is actually over there by a few feet. Each individual discrepancy is small enough that you might dismiss it. But when you notice several of them, all suggesting the map is slightly off, you start to wonder, maybe the map isn't the final word. Maybe there's a more detailed map that would account for these small discrepancies. That's exactly where physics is right now. We have an incredibly accurate map of reality. But there are whispers, hints, suggestions from multiple independent experiments that the map might not be complete. And those whispers are what we're going to explore next. Because what's hiding in the gaps between prediction and measurement might be more important than everything the standard model already explains. So we've established that the standard model is extraordinary. It predicts the behavior of fundamental particles with a precision that no other scientific theory has ever achieved. And yet, physicists are almost certain it's not the final answer. The theoretical reasons for this are compelling on their own. The absence of gravity, the unexplained parameters, the lack of deep unification. But theories are ultimately judged by experiment, and this is where things get genuinely exciting. Because over the past couple of decades, experiments have started, producing results that don't quite match what the standard model predicts. Not wildly different, not dramatically wrong, just slightly off, persistently, stubbornly, maddeningly off. And these small deviations might be the most important clues in all of physics. Let's start with the muon. Remember, the muon is essentially a heavier version of the electron. It has the same electric charge, the same spin, the same interactions with forces. It's just about 207 times more massive. Nobody knows why it exists. When the muon was first discovered in 1936, the physicist Isidore Isaac Rabi famously responded with, "Who ordered that?" It seemed like an unnecessary particle, a heavier copy of the electron that served no obvious purpose. But the muon turned out to be incredibly useful for testing the standard model. And the reason has to do with something called the anomalous magnetic moment. Every charged particle that spins behaves like a tiny magnet. The strength of this magnetism can be characterized by a number that physicists call G. For a simple spinning charged particle described by basic quantum mechanics, G should equal exactly 2. But the real world is more complicated than that. In quantum field theory, the vacuum of space isn't truly empty. It's a seething, churning sea of virtual particles that constantly pop into existence and vanish again. These virtual particles briefly appear, interact with the muon, and then disappear. Each of these fleeting interactions nudges the muon's magnetic moment slightly away from the simple prediction of 2. The total effect of all these virtual interactions is called the anomalous magnetic moment, and physicists denote it as G-2 because they're measuring how much G deviates from 2. Now here's the key point. The standard model allows you to calculate this anomalous magnetic moment. You add up the contributions from every type of virtual particle interaction. Photons, quarks, gluons, W and Z, bosons, Higgs bosons, neutrinos, everything the standard model contains. It's an incredibly difficult calculation that has taken decades of work by hundreds of theoretical physicists. But the result is a specific number, a prediction for how much the muon's magnetism should deviate from simple expectations. And this is where it gets interesting. You can also measure G-2 in the laboratory. You create muons in a particle accelerator, inject them into a precisely controlled magnetic field, and watch them wobble. The rate of this wobble depends on the muon's anomalous magnetic moment. By measuring the wobble extremely carefully, you can determine G-2 with remarkable precision. The experiment to do this is being conducted at Fermi National Accelerator Laboratory, Fermilab, just outside Chicago. The muon G-2 experiment uses a 50-foot diameter superconducting magnetic storage ring. Muons are injected into this ring where they circulate at nearly the speed of light, wobbling as they go. Sensitive detectors around the ring measure the wobble with extraordinary accuracy. In 2021, the Fermilab team announced their first results. They had measured the muon's anomalous magnetic moment to incredible precision. And the number they got didn't match the standard model prediction. It was slightly higher than what the theory said it should be. Not by a lot. We're talking about a discrepancy in the 9th decimal place. But at the level of precision these experiments achieve, that discrepancy is significant. By 2023, after combining multiple runs of data, the experimental measurement of the muon's anomalous magnetic moment had reached a precision of about 200 parts per billion, and the discrepancy with the standard model prediction persisted. The difference between theory and experiment corresponds to what physicists call roughly a 5 sigma deviation, depending on which theoretical calculation you use. Particle physics, a 5 sigma result means the probability of this discrepancy being a random fluctuation is about 1 in 3.5 million. That's the threshold physicists traditionally use to claim a discovery. But there's a complication, and it's important to be honest about it. The standard model prediction for the muon G-2 is extremely difficult to calculate. The hardest part involves contributions from the strong force, specifically something called hadronic vacuum polarization. This is where virtual quarks and gluons briefly pop out of the vacuum and influence the muon's magnetism. Calculating this precisely requires dealing with the strong force at low energies, which is notoriously difficult. There are 2 main approaches to this calculation. One uses experimental data from electron-positron collisions to estimate the hadronic contribution. This approach has been the standard for years, and it gives a prediction that disagrees with the Fermilab measurement. The other approach uses a computational technique called lattice quantum chromodynamics, where physicists simulate the strong force on powerful supercomputers by dividing space and time into a discrete grid and calculating the behavior of quarks and gluons directly. Some lattice calculations, particularly one from the BMW collaboration published in 2021, give a result that's closer to the experimental measurement, potentially reducing the discrepancy. So the situation is genuinely uncertain. If the traditional calculation is correct, then the muon G-2 result is a clear signal of new physics. Something beyond the standard model, some unknown particle or force, is interacting with the muon and nudging its magnetic moment. If the lattice calculation is correct, then the discrepancy might be smaller than we thought, and the standard model might still be consistent with the data. Physicists are working hard to resolve this. Multiple lattice groups around the whole world are performing independent calculations. New experimental data from Fermilab continues to be collected and analyzed. Within the next few years, we should have a much clearer picture. But as of right now, the muon G-2 anomaly remains one of the most tantalizing hints of physics beyond the standard model. It's a whisper that refuses to be silenced. Now let's move to a completely different set of experiments. At the Large Hadron Collider at CERN, physicists have been studying something called flavor anomalies. And these anomalies, while more subtle than the muon G-2 story, are equally intriguing. In particle physics, flavor refers to the different types of quarks and leptons. The 6 quarks, up, down, charm, strange, top and bottom, each have a different flavor. The 3 charged leptons, electron, muon, and tau, also have different flavors. One of the fundamental principles built into the standard model is something called lepton flavor universality. This principle says that the 3 charged leptons, electron, muon, and tau, are identical in every way except their mass. The forces don't care which lepton they're interacting with. A W boson decaying into an electron should behave in exactly the same way as a W boson decaying into a muon, after you account for the difference in mass. The universe should treat electrons and muons as interchangeable partners. This is a very specific prediction, and it can be tested experimentally. One way to test it is to look at certain decays of particles called B-mesons. A B-meson is a particle that contains a bottom quark paired with another quark. B-mesons are produced in enormous quantities at the Large Hadron Collider, and they decay through the weak force into lighter particles. The LHCb experiment at CERN is specifically designed to study these decays with extraordinary precision. Over the years, the LHCb collaboration has measured ratios of decay rates that should, according to lepton flavor universality, be exactly equal to 1. For instance, they measured a quantity called R sub k, which compares the rate at which a particular B-meson decay produces muons versus the rate at which it produces electrons. According to the standard model, this ratio should be very close to 1. For several years, LHCb measurements consistently showed values of R sub k and related quantities that were below 1. The decays seemed to produce fewer muons than expected. It was as if something in nature was distinguishing between electrons and muons, violating the principle that the forces should treat them equally. This was deeply suggestive because the standard model has no mechanism for this kind of distinction. If the effect were real, it would require new physics, some new particle or interaction that couples differently to muons than to electrons. However, in 2022 and 23, LHCb released updated analyses with improved methods for handling systematic uncertainties, particularly related to how electrons are detected compared to muons. These updated measurements shifted closer to the standard model prediction. The most dramatic discrepancies were reduced. Some physicists interpreted this as the anomaly disappearing. Others pointed out that while the individual measurements of R sub k moved closer to 1, other related measurements and angular distributions in B-meson decays still show patterns that are difficult to explain within the standard model. The situation with flavor anomalies is messy in the best possible scientific sense. The data doesn't give a clean, unambiguous answer. Some measurements have come back into agreement with the standard model. Others remain in tension. The overall pattern across multiple different observables still shows intriguing deviations from standard model predictions when you look at them collectively rather than individually. It's like having a dozen slightly bent arrows. No single arrow is dramatically off target, but they all seem to bend in the same direction. That pattern is what keeps physicists interested. The Belle 2 experiment in Japan, which began collecting data in 2019, is designed to study many of the same processes with different techniques and different sources of systematic uncertainty. Over the coming years, Belle 2 will provide independent measurements that should either confirm or refute the patterns seen at LHCb. If both experiments see the same deviations, the case for new physics becomes much stronger. If Belle 2 sees perfect agreement with the standard model, the LHCb anomalies might fade away. Now let's turn to what is arguably the most clear-cut crack in the standard model. Not an anomaly that might go away with better data, not a tension at the edge of statistical significance, but a confirmed, undeniable fact that the standard model got wrong: neutrino masses. Remember what I said earlier about neutrinos? They're ghostly particles that barely interact with matter. In the original formulation of the standard model, neutrinos were assumed to be completely massless. This wasn't an arbitrary choice. It followed naturally from the mathematical structure of the theory. The way the standard model is constructed, there's no mechanism to give neutrinos mass. They should weigh exactly 0, but they don't. The story of how we discovered this is one of the great detective stories in physics. It begins with the sun. The sun produces enormous numbers of neutrinos through the nuclear fusion reactions in its core. Physicists can calculate exactly how many neutrinos the sun should produce based on our understanding of nuclear physics and the sun's temperature and composition. In the late 1960s, an American physicist named Raymond Davis Jr. built a detector to measure these solar neutrinos. His detector was a tank filled with 100,000 gallons of dry cleaning fluid, perchloroethylene, buried deep in the home state gold mine in South Dakota. When a neutrino interacted with a chlorine atom in the fluid, it would transform it into an atom of argon. By counting the argon atoms, Davis could count the neutrinos. The results were shocking. Davis detected only about 1/3 the number of neutrinos that theoretical models predicted. This was deeply troubling. Either our understanding of the sun was fundamentally flawed, or something was happening to the neutrinos on their way from the sun's core to the detector in South Dakota. At first, people assumed either the solar models were wrong or there was something wrong with the experiment. But other experiments using completely different detection methods confirmed the deficit. The sun was producing fewer electron neutrinos than expected. This became known as the solar neutrino problem, and it persisted for over 30 years, baffling physicists worldwide. The solution turned out to be extraordinary. The neutrinos weren't missing, they were transforming. As electron neutrinos traveled from the sun's core to Earth, they were spontaneously changing into muon neutrinos and tau neutrinos. Davis's detector could only see electron neutrinos, so the ones that had transformed were invisible to it. This process is called neutrino oscillation, and it was confirmed definitively in 2001 by the Sudbury Neutrino Observatory in Canada. The SNO detector could detect all 3 types of neutrinos, and it showed that the total number matched the solar models perfectly. The electron neutrinos were indeed transforming into other flavors during their journey from the Sun. But here's the crucial point. For neutrinos to oscillate, to change from one flavor to another, they must have mass. Massless particles cannot oscillate. This is a direct consequence of quantum mechanics. The mathematics is unambiguous. Neutrino oscillation requires neutrino mass, and neutrino oscillation has been confirmed by multiple independent experiments studying neutrinos from the Sun, from nuclear reactors, from cosmic ray interactions in the atmosphere, and from particle accelerators. This is not a subtle anomaly or a marginal tension. This is a fact. Neutrinos have mass. The standard model says they shouldn't. The standard model is wrong about this. It's the one confirmed place where the standard model's predictions have been definitively contradicted by experiment. Now, to be fair, it's possible to extend the standard model to include neutrino masses. You can add new terms to the equations, new particles like right-handed neutrinos, and make it work. But these additions aren't natural. They don't arise from the existing structure of the theory. They have to be grafted on, like adding an extra room to a house by building an awkward extension. The fact that neutrino masses require going beyond the standard model's original framework tells us something important. The standard model, as originally conceived, is incomplete. There's physics out there that it doesn't capture, and there are deep mysteries about neutrino masses that remain unsolved. The masses of neutrinos are extraordinarily small, at least 1 million times lighter than the electron, which is itself the lightest massive particle in the standard model. Why are neutrino masses so tiny compared to everything else? There's no explanation within the standard model. One popular idea is something called the seesaw mechanism, which proposes that neutrinos are light because there are extremely heavy partner particles, so heavy they've never been detected, that push the neutrino masses down. But this is speculative. We don't know if these heavy partners exist. We also don't know the absolute masses of neutrinos. Oscillation experiments tell us the differences between the masses of the 3 neutrino types, but not the overall scale. The lightest neutrino could be nearly massless, or it could have a small but measurable mass. Experiments, like Katrin in Germany, are trying to determine this by studying the energy spectrum of electrons emitted in tritium beta decay. The results so far have set an upper limit, but haven't pinned down the exact mass. There's also a mystery about whether neutrinos are their own antiparticles. Most particles have distinct antiparticles. The electron has the positron. The up quark has the anti-up quark. But neutrinos, because they carry no electric charge, might be their own antiparticles. A particle that is its own antiparticle is called a Majorana particle, named after the Italian physicist Ettore Majorana, who proposed the idea in 1937. If neutrinos are Majorana particles, it would have profound implications for physics and could help explain the matter-antimatter asymmetry in the universe. Experiments searching for a process called neutrinoless double beta decay are looking for evidence of this. So far, no definitive signal has been found, but the search continues with ever more sensitive detectors. The neutrino mass problem is the clearest evidence that the standard model needs to be extended. It's not a hint. It's not a whisper. It's a confirmed fact that points firmly toward new physics. Let me now tell you about one more anomaly that generated enormous excitement when it was announced, though its status has become more complicated over time. In April of 2022, the CDF2 collaboration at Fermilab published a measurement of the mass of the W boson that stunned the physics community. The W boson, as I described earlier, is one of the carriers of the weak nuclear force. Its mass is a critical parameter of the Standard Model. The Standard Model doesn't predict the W boson mass from scratch, but once you know a handful of other parameters, the mass of the top quark, the mass of the Higgs boson, the strength of the electromagnetic and weak forces, the theory predicts the W boson mass with high precision. The predicted value is about 80.357 billion electron volts divided by the speed of light squared. This might sound like an unusual way to express mass, but in particle physics, mass and energy are interchangeable thanks to Einstein's famous equation, so particle masses are typically expressed in units of energy. The CDF2 experiment had been collecting data at Fermilab's Hadron Collider from 2002 to 2011. After years of painstaking analysis, the team announced their final measurement of the W boson mass. The number they got was 80.4335 billion electron volts. That's about 76 million electron volts higher than the Standard Model prediction. The uncertainty in their measurement was only about 9 million electron volts, meaning the discrepancy was about 7 standard deviations away from the prediction. 7 sigma. In particle physics, that's enormous. A 5 sigma result is considered definitive. 7 sigma should be beyond any reasonable doubt. If the CDF2 measurement is correct, it would be one of the most significant experimental results in decades. A W boson mass that disagrees with the Standard Model prediction at this level would mean something is fundamentally wrong with theory. Some new particle or force is contributing to the W boson mass, shifting it from its predicted value. It would be clear, unambiguous evidence of physics beyond the Standard Model. But there's a significant complication. The CDF2 measurement disagrees not only with the Standard Model prediction, but also with most other measurements of the W boson mass. The ATLAS experiment at the Large Hadron Collider measured the W boson mass and got a value much closer to the Standard Model prediction. The LHCb experiment measured it and also got a value consistent with the Standard Model. An earlier measurement from the D0 experiment at the same Hadron Collider where CDF2 operated also found a lower value. So we have a situation where one very precise measurement says the W boson mass is higher than predicted, while several other measurements say it's about where the Standard Model expects it to be. This creates tension, not just between experiment and theory, but between different experiments. What's going on? There are several possibilities. The CDF2 measurement could be correct, and the other experiments could have unknown systematic errors that pulled their measurements too low. This seems unlikely given that multiple independent experiments agree with each other and with the Standard Model, while CDF2 stands alone. Alternatively, the CDF2 analysis might have an undetected systematic error that shifted their result too high. Measuring the W boson mass is extraordinarily difficult. It requires understanding every aspect of the detector with extreme precision, from how particles deposit energy in the calorimeters to how the detector's magnetic field affects particle trajectories. A tiny miscalibration or an unaccounted for effect could shift the result. As of now, the physics community has not reached a consensus. The CDF2 result hasn't been retracted. The team stands by their analysis, but the weight of evidence from other experiments doesn't support such a large deviation. This is how science works. A single dramatic result, no matter how statistically significant, needs to be confirmed by independent measurements before it's accepted. The coming years will bring new, more precise measurements from the Large Hadron Collider that should settle the question. Let me step back and look at the bigger picture. We've discussed 4 different experimental anomalies. The muon G-2 measurement showing a possible deviation from the standard model prediction. The flavor anomalies at the LHCb experiment suggesting possible violations of lepton flavor universality. The confirmed fact that neutrinos have mass, which the standard model cannot naturally accommodate, and the CDF2W boson mass measurement that disagrees with both the standard model and other experiments. These anomalies are very different from each other. They come from different experiments, studying different particles using different techniques. Some are strong and confirmed, like neutrino masses. Some are tantalizing but uncertain, like the muon G-2. Some are controversial, like the W boson mass. Some are evolving as new data comes in, like the flavor anomalies. But here's what makes this moment in physics so fascinating. Even though no single anomaly, with the exception of neutrino masses, constitutes definitive proof of new physics, the fact that there are multiple independent hints all pointing away from the standard model is deeply suggestive. If the standard model were truly the final theory, you would expect all measurements to agree with it, within the expected statistical fluctuations. Instead, we see a pattern of small deviations in multiple places. It's like a doctor examining a patient. No single symptom is alarming on its own. A slightly elevated temperature could be nothing. A mild headache could be stress. A bit of fatigue could be lack of sleep. But when you see all of these symptoms together, you start to suspect something underlying is going on. Something you haven't diagnosed yet. That's how physicists feel about the standard model right now. The individual anomalies might each have innocent explanations, but the overall pattern of tension suggests the theory is missing something. And remember, these experimental anomalies exist on top of the theoretical problems we already discussed. The inability to include gravity, the unexplained parameters, the 3 generations of matter with no explanation for why 3, the hierarchy problem, which is the bizarre and unexplained fact that the Higgs boson mass is so much lighter than what naive calculations suggest it should be. When you combine the theoretical gaps with the experimental tensions, the case for physics beyond the standard model becomes compelling. The standard model isn't wrong. Let me be very clear about that. It's not wrong in the way that older theories were wrong. The geocentric model of the solar system was wrong. Phlogiston theory of combustion was wrong. Those theories made predictions that were contradicted by observations, and they had to be abandoned. The standard model is different. Its predictions are correct to an extraordinary degree of precision across an enormous range of phenomena. It's one of the most successful theories in the history of science, but it's incomplete. It's like Newtonian mechanics. Newton's laws of motion and gravity were spectacularly successful for over 2 centuries. They predicted the orbits of planets, the trajectories of cannonballs, the tides of the ocean. They worked beautifully for everything people could test them against. But they weren't the final answer. In extreme conditions, at very high speeds, or in very strong gravitational fields, Newton's laws break down. Einstein's theories of special and general relativity replace them, not by contradicting them, but by revealing them to be an approximation of something deeper. Newton's laws are still correct for everyday speeds and normal gravitational fields. They're a limiting case of Einstein's more complete theory. The Standard Model is almost certainly in the same position today. It's extraordinarily accurate in its domain, but it's an approximation of something deeper. Something that includes gravity, something that explains the parameters, something that accounts for neutrino masses naturally, something that resolves the anomalies we're seeing in experiments. The cracks we're finding aren't signs that the Standard Model has failed. They're signposts pointing toward the next, deeper theory. The theory that the Standard Model is merely an approximation of. The question is, what is that deeper theory, and how do we find it? Because right now, we're in one of the most exciting and profoundly uncertain periods in the entire history of physics. We have a theory that works almost perfectly, but not quite. We have hints from experiments that something new is out there, but we don't yet know what it is. We're standing at the edge of known physics, peering out into the darkness, trying to make out the shape of whatever comes next. So far, we've been talking about cracks, small discrepancies between what the Standard Model predicts and what experiments measure. Subtle tensions that might point toward new physics. But now we need to talk about something much bigger. Not cracks in the Standard Model, but gaping holes. Entire categories of phenomena that the Standard Model doesn't just get slightly wrong. It doesn't address them at all. These aren't whispers from experiments suggesting something might be off. These are screaming contradictions between what we observe in the universe and what the Standard Model is capable of explaining. And they suggest that the Standard Model, despite its extraordinary precision in the domain it covers, is missing most of reality. Let's start with the biggest one, dark matter. Look up at the night sky on a clear night, and you see stars. Thousands of them. Each one a massive ball of fusing hydrogen, pouring light into the darkness. These stars are made of the same particles the Standard Model describes. Quarks, electrons, photons, gluons. The Standard Model handles them beautifully. But here's the problem. All the stars you can see, all the stars in every galaxy, all the gas and dust between them, all the planets and moons and asteroids and comets, every bit of ordinary matter in the entire universe makes up only about 5% of the total mass and energy content of the cosmos. 5%. That means 95% of the universe is made of something the Standard Model knows nothing about. About 27% of the universe consists of dark matter. We call it dark because it doesn't emit light, absorb light, or interact with light in any detectable way. It's invisible. You can't see it with any telescope, no matter how powerful, because it doesn't interact with electromagnetic radiation at all. It's not dark in the sense that it's hidden in shadows. It's dark in the sense that it's fundamentally transparent to every form of light we know. So how do we know it exists? Because we can see what it does to things around it. Dark matter has gravity. It pulls on ordinary matter. And the effects of that gravitational pull are visible everywhere we look on cosmic scales. The first strong evidence came in the 1970s from an American astronomer named Vera Rubin. Rubin was studying the rotation of spiral galaxies. In a spiral galaxy, stars orbit the galactic center, much like planets orbit the sun. Based on the visible mass of a galaxy, the mass you can see in stars and gas, you can predict how fast stars at different distances from the center should be moving. Stars near the center should orbit quickly because there's a lot of mass inside their orbit pulling them inward. Stars farther out should orbit more slowly because the gravitational pull weakens with distance. This is exactly what happens in our solar system. Mercury, the closest planet to the sun, orbits at about 47 kilometers per second. Neptune, way out at the edge, orbits at only about 5 kilometers per second. The farther you are from the central mass, the slower you go. But when Rubin measured the orbital speeds of stars in spiral galaxies, she found something that didn't make sense. The stars far from the galactic center were moving just as fast as the stars near the center. In some cases, they were moving even faster. According to Newton's laws and everything we know about gravity, this should be impossible. If the only mass in the galaxy were the visible stars and gas, those outer stars should be moving much more slowly. They were moving so fast that they should have been flung out of the galaxy entirely, like a car taking a curve too fast. The galaxy's visible mass didn't provide enough gravitational pull to hold them in orbit. The only explanation that works is that there's far more mass in the galaxy than what we can see. A vast halo of invisible matter surrounding the galaxy, extending far beyond the visible stars, providing the extra gravitational pull needed to keep those fast-moving outer stars in their orbits. This invisible mass is dark matter, and there's a lot of it. In a typical galaxy, dark matter outweighs ordinary visible matter by a factor of about 6 to 1. The stars and gas that make up the visible part of a galaxy are just the luminous tip of a much larger dark matter iceberg. Since Rubin's work, evidence for dark matter has accumulated from multiple independent sources. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, contain far more mass than the visible galaxies account for. We know this because of gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects bend the path of light, passing near them. When we observe distant galaxies behind a galaxy cluster, their images are distorted, bent, and stretched by the cluster's gravity. The amount of distortion tells us how much mass the cluster contains, and the answer is always the same: far more mass than the visible matter can explain. The cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, provides perhaps the most compelling evidence of all. This radiation was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. The pattern of tiny temperature fluctuations in this radiation encodes information about the composition of the early universe. By analyzing these patterns with extraordinary precision, as the Planck satellite did between 2009 and 2013, cosmologists can determine how much ordinary matter, dark matter, and dark energy the universe contains. The results are consistent with every other line of evidence. About 5% ordinary matter, about 27% dark matter, about 68% dark energy. The evidence for dark matter is overwhelming. It comes from galactic rotation curves, galaxy cluster dynamics, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, and the way galaxies formed and evolved over cosmic time. Every one of these independent lines of evidence points to the same conclusion. There's far more matter in the universe than what we can see, and this invisible matter doesn't interact with light. And the standard model has absolutely no explanation for it. The standard model contains a list of fundamental particles. We discussed them earlier. Quarks, leptons, photons, gluons, W, and Z bosons, and the Higgs boson. None of these particles behave like dark matter. Dark matter doesn't interact electromagnetically, which rules out anything with electric charge. It doesn't interact through the strong force, which rules out quarks and gluons. It's stable, persisting for billions of years, which rules out most unstable particles. Whatever dark matter is made of, it's not any particle in the standard model. This is not a minor gap. This is the standard model failing to account for about 85% of all the matter in the universe. Imagine you had a theory of cooking that perfectly explained how to prepare 5% of all known foods, but was completely silent about the other 95%. You might admire its accuracy within its domain, but you wouldn't call it a complete theory of cooking. The standard model is in a similar position. It describes the behavior of ordinary matter with breathtaking precision. But ordinary matter is just a small fraction of what the universe actually contains. Physicists have proposed many candidates for dark matter particles. The most popular for decades were WIMPs, weakly interacting massive particles. These would be heavy particles that interact through the weak force and gravity, but not through electromagnetism or the strong force. WIMPs arise naturally in many theoretical extensions of the standard model, which made them an attractive candidate. But despite decades of searching with increasingly sensitive detectors buried deep underground to shield them from cosmic rays and other interference, no WIMP has ever been detected. Experiments like Xenon, Lux Zeppelin, and Pandax have set extraordinarily tight limits on how strongly WIMPs can interact with ordinary matter, ruling out large swaths of the parameter space where WIMPs were expected to lurk. Other candidates include axions, hypothetical, extremely light particles originally proposed to solve a different problem in quantum chromodynamics. There are also sterile neutrinos, heavier cousins of the ordinary neutrinos that would interact with matter only through gravity. And there are more exotic possibilities, from primordial black holes to particles from hidden sectors of physics that we've never encountered. Each of these candidates requires physics beyond the standard model. Finding dark matter won't just tell us what the universe is made of. It will tell us what the standard model is missing. Now let's move to another enormous mystery, one that's even more unsettling in some ways because it deals with why we exist at all. The matter-antimatter asymmetry. For every type of particle in the standard model, there's a corresponding antiparticle. The electron has the positron. The up quark has the anti-up quark. The proton has the antiproton. Antiparticles are identical to their counterparts in every way, except they carry opposite charges. When a particle meets its antiparticle, they annihilate each other, converting all their mass into pure energy in the form of photons. This process is extraordinarily efficient. A single gram of matter annihilating with a single gram of antimatter would release roughly 3 times the energy of the Hiroshima bomb. According to our best understanding of the Big Bang, the early universe was unimaginably hot and dense. In those first moments, energy was constantly converting into pairs of particles and antiparticles, and those particles and antiparticles were constantly annihilating back into energy. This is a natural consequence of Einstein's equation relating mass and energy. At sufficiently high temperatures, energy spontaneously creates matter and antimatter in exactly equal amounts. For every quark that was created, an antiquark was created alongside it. For every electron, a positron. Perfect symmetry. Equal amounts of matter and antimatter. But here's the problem. If the Big Bang produced exactly equal amounts of matter and antimatter, then as the universe cooled, all the matter and antimatter should have annihilated each other completely. Every particle should have found its antiparticle partner, and they should have mutually destroyed each other, leaving behind nothing but a universe filled with photons. No atoms, no stars, no planets, no people, just light. Pure radiation filling an empty cosmos. Obviously, that's not what happened. We're here. The universe is full of matter. Stars, galaxies, planets, you and me. We exist. And we're made of matter, not antimatter. Somehow, in the early universe, there was a tiny imbalance. For every billion antiparticles, there were about 1,000,000,001 particles. That tiny excess, roughly 1 extra matter particle for every billion matter antimatter pairs, survived the Great Annihilation. All the match pairs destroyed each other, converting into photons. But that tiny leftover, that 1 in a billion surplus of matter, is what everything in the universe today is made from. Every star, every galaxy, every atom in your body is the residue of that minuscule imbalance. The question is, where did that imbalance come from? What process in the early universe favored matter over antimatter by this tiny but crucial amount? The Standard Model does contain a mechanism for matter-antimatter asymmetry. It's called CP violation, and it was first observed experimentally in 1964 in the decay of particles called kaons. CP violation means that certain processes involving particles behave differently than the equivalent processes involving antiparticles. The laws of physics are not perfectly symmetric between matter and antimatter. There's a slight difference, a subtle bias, but here's the thing. The amount of CP violation in the Standard Model is far, far too small to explain the observed matter-antimatter asymmetry. When you do the calculation, the Standard Model produces an imbalance that's about 10 orders of magnitude, 10 billion times smaller than what's needed to explain the amount of matter we see in the universe. It's not even close. The Standard Model knows that matter and antimatter aren't perfectly symmetric, but the asymmetry it produces is absurdly inadequate to explain our existence. This means there must be additional sources of CP violation beyond what the Standard Model contains. Some process, some interaction, some new physics that operated in the early universe and tipped the balance in favor of matter over antimatter far more strongly than the Standard Model can account for. Without this unknown physics, we shouldn't exist. The universe should be empty of matter. The fact that you're here, that anything is here, is evidence that the standard model is missing something fundamental about how the universe works. Experiments at the Large Hadron Collider and a dedicated B-factory experiments like Bell 2 in Japan are searching for new sources of CP violation in the decays of various particles. If they find CP violation that exceeds standard model predictions, it could point toward the new physics responsible for the matter-antimatter asymmetry. But so far, while measurements continue to improve in precision, no clear evidence of new CP violation beyond the standard model has been found. The source of the matter-antimatter asymmetry remains one of the deepest mysteries in physics. Now, let's talk about dark energy, the most mysterious component of the universe. If dark matter is the standard model's biggest blind spot in terms of matter, dark energy is its biggest blind spot in terms of, well, everything. In 1998, two independent teams of astronomers made a discovery that shocked the world. They were studying distant Type 1a supernovae, a particular type of stellar explosion that serves as a cosmic distance marker because they all explode with roughly the same intrinsic brightness. By measuring how bright these supernovae appeared and comparing that to how bright they should be based on their known intrinsic luminosity, astronomers could calculate how far away they were. And by measuring the redshift of the light from these supernovae, they could determine how fast the universe was expanding when the light was emitted. What they expected to find was that the expansion of the universe was slowing down. This made sense. The universe is full of matter, and matter has gravity, and gravity pulls things together. The expansion that began with the Big Bang should have been gradually decelerating as the mutual gravitational attraction of all the matter in the universe worked to slow it down. What they actually found was the opposite. The expansion of the universe isn't slowing down, it's speeding up. The universe is expanding faster and faster over time. Something is pushing space apart, counteracting gravity, driving galaxies away from each other at an ever-increasing rate. This was so unexpected that both teams initially thought they'd made a mistake. They checked their data, rechecked their calibrations, looked for errors, but the result held. The universe's expansion is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery. The mysterious force driving this acceleration is what we call dark energy, and we know almost nothing about it. We know it makes up about 68% of the total energy content of the universe. We know it has a repulsive gravitational effect, pushing space apart rather than pulling it together. We know it operates on the largest cosmic scales, becoming significant only at distances of hundreds of millions of light years or more. And that's essentially all we know. The standard model has nothing to say about dark energy. It's a theory of particle physics, of the interactions between subatomic particles. It doesn't address the large-scale behavior of space-time. Dark energy is really the domain of cosmology and general relativity rather than particle physics. But here's where things get embarrassing for theoretical physics. There's a concept in quantum field theory called vacuum energy. Even in perfectly empty space, the quantum fields that permeate the universe have a minimum energy. Virtual particles are constantly popping in and out of existence, and this activity contributes a baseline energy to the vacuum itself. This vacuum energy should, in principle, act like dark energy. It should have a gravitational effect, pushing space apart. The problem is when you try to calculate how much vacuum energy quantum field theory predicts. The answer you get is enormous. Not just a little too big, absurdly, catastrophically too big. The predicted vacuum energy is about 120 orders of magnitude larger than what we observe. That's a 1 followed by 120 zeros times 2 large. This is sometimes called the worst prediction in the history of physics. If the vacuum energy were really that large, the universe would have expanded so rapidly that no structures could ever have formed. No galaxies, no stars, no planets, no life. The universe would be empty, expanding at an inconceivable rate. Something is cancelling out almost all of that vacuum energy, leaving behind just a tiny residual amount that we observe as dark energy. But nobody knows what that something is. There's no known mechanism that would reduce the vacuum energy by a factor of 10 to the 120 while leaving a tiny amount behind. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. It sits right at the intersection of quantum mechanics and gravity, exactly the place where our theories break down. Now, let's discuss the hierarchy problem, because this is one of the most puzzling aspects of the Standard Model, and it connects to several of the other mysteries we've been discussing. The hierarchy problem is about a dramatic, unexplained mismatch between two fundamental energy scales in physics. On one hand, you have the electroweak scale, the energy scale associated with the weak nuclear force and the Higgs mechanism. This scale is characterized by the mass of the Higgs boson, which is about 125 billion electron volts. On the other hand, you have the Planck scale, the energy scale at which gravity becomes as strong as the other forces and quantum gravitational effects become important. The Planck scale is about 10 to the 19th billion electron volts. That's roughly 10 million billion times higher than the electroweak scale. Why is there such an enormous gap between these two scales? Why is gravity so spectacularly weaker than the other forces? When you hold a refrigerator magnet against a refrigerator door, the electromagnetic force of that tiny magnet is overcoming the gravitational pull of the entire planet Earth. The electromagnetic force between two protons is about 10 to the 36 times stronger than the gravitational force between them. That's a trillion times stronger. This ratio is bizarre. It's unnatural in a technical sense that physicists use to describe fine-tuning. The hierarchy problem becomes even more acute when you think about quantum corrections to the Higgs boson mass. In quantum field theory, every particle's mass receives contributions from virtual particle interactions. These contributions can be very large. For the Higgs boson, the quantum corrections to its mass from virtual particles should naturally push it up to something near the Planck scale, making it enormously heavy. The only way to get the Higgs mass to be at the electroweak scale, where we observe it, is if there are extraordinary cancellations between different contributions. Positive contributions from one type of virtual particle need to almost perfectly cancel negative contributions from another type, leaving behind only a tiny residual mass. The degree of cancellation required is staggering. The different contributions need to cancel to about 1 part in 10 to the 34. That's like two numbers, each with 34 digits that happen to be almost exactly equal, so that when you subtract one from the other, you get a number with only a few digits. This seems incredibly unlikely to occur by chance. It looks like fine-tuning, and physicists are deeply uncomfortable with fine-tuning because it suggests there's a deeper explanation we haven't found yet. This is why many physicists expected to find new particles at the Large Hadron Collider. Theoretical proposals like supersymmetry, which we'll explore in detail later, were designed in part to solve exactly this problem by introducing new particles whose quantum effects would naturally stabilize the Higgs mass. But so far, the Large Hadron Collider has found no such particles. The hierarchy problem remains wide open. The hierarchy problem might be telling us something profound about the structure of physics at high energies. It might be pointing toward new particles and forces that stabilize the Higgs mass naturally. Or it might be telling us that our expectations about naturalness and fine-tuning are wrong, that nature simply doesn't care about what physicists find aesthetically pleasing. Either way, it represents a deep mystery that the Standard Model cannot resolve on its own. And finally, there's the most fundamental missing piece of all. We discussed earlier how the Standard Model and general relativity are fundamentally incompatible. How the mathematical techniques that work so well for the other three forces produce infinite, nonsensical answers when applied to gravity. But this incompatibility isn't just an abstract theoretical concern. There's a specific scale at which it becomes a concrete barrier to understanding reality. It's called the Planck scale. The Planck length is about 1.6 times 10 to the negative 35 meters. That's about 10 to the negative 20 times the size of a proton. Unimaginably small. The Planck energy, the energy at which quantum gravitational effects become significant, is about 10 to the 19th billion electron volts. For comparison, the Large Hadron Collider operates at about 13,000 billion electron volts. The Planck energy is roughly 1,000,000 billion times higher than what we can currently probe. We're not even close. This gulf between the energies we can reach and the energies where quantum gravity matters is staggering. It means we cannot directly test any theory of quantum gravity with current technology. We cannot calculate what happens at the center of a black hole, where matter is crushed to densities so extreme that both quantum mechanics and gravity must be important. We cannot describe the first instant of the Big Bang when the entire observable universe was compressed into a region smaller than an atom. Our two most fundamental theories give conflicting stories about these extreme environments, and we have no way to reconcile them. Until we find a theory that unifies quantum mechanics and gravity, a theory of quantum gravity, our understanding of the universe's most dramatic moments remains fundamentally incomplete. We have promising approaches, which we'll discuss later, but nothing that's been confirmed by experiment. So let's take stock of where we are. The Standard Model accurately describes the interactions of fundamental particles with extraordinary precision. But the universe contains phenomena that the Standard Model cannot explain at all. Dark matter makes up about 27% of the universe's total energy content, and no Standard Model particle can account for it. Dark energy makes up about 68%, and the Standard Model's only connection to it, vacuum energy, gives an answer that's off by 120 orders of magnitude. The matter-antimatter asymmetry that allows anything to exist at all requires physics beyond what the standard model provides. The hierarchy problem suggests that the Higgs boson mass is unnaturally fine-tuned, pointing toward unknown stabilizing physics. And gravity, the force that shapes the large-scale universe, cannot be incorporated into the standard model's framework at all. When you add it all up, the standard model accurately describes about 5% of the universe's content. The other 95% is dark matter and dark energy, both of which lie entirely outside its scope. And even within that 5%, there are phenomena like the matter-antimatter asymmetry and neutrino masses that require extensions beyond the original theory. The standard model is like a flashlight, illuminating a small patch of a vast dark room. Within that patch, it shows you everything with extraordinary clarity. Every detail, every texture, every color is visible and precisely described. But step outside the beam and you're in total darkness. You know there's more out there because you can hear things moving, feel the floor extending beneath your feet, sense the walls in the distance, but you can't see any of it. The flashlight is brilliant within its circle of light, but the room is much, much bigger than what the beam reveals. This is not a failure of the standard model, it's a limitation, a very important distinction. The standard model was never designed to explain dark matter or dark energy or gravity at the quantum level. It was designed to describe the fundamental particles and their interactions through 3 of the 4 forces, and it does this spectacularly well. The fact that there's more to the universe than what it covers doesn't make it wrong. It makes it incomplete, and recognizing that incompleteness is the first step toward finding whatever comes next. Because something does come next. The universe is telling us, through dark matter and dark energy and the matter-antimatter asymmetry and all the other missing pieces, that there are aspects of reality we haven't discovered yet. New particles, new forces, new principles that we haven't imagined. The standard model is almost certainly an approximation of a deeper, more complete theory. A theory that would explain not just the 5% of the universe we currently understand, but all of it. The question is whether we can find that theory. And that's what brings us to the search itself. So we know the standard model is incomplete. We know it can't explain dark matter, dark energy, the matter-antimatter asymmetry, neutrino masses, or gravity at the quantum level. We know there are experimental anomalies that hint at new physics lurking just beyond the theory's reach. The question now is, what do we do about it? How do physicists actually search for whatever lies beyond the standard model? And what might that new physics look like? This is where the story shifts from diagnosis to exploration. Because physicists aren't sitting around hoping the answers will fall from the sky. They're actively hunting for new physics using some of the most extraordinary machines and experiments ever conceived by human beings. And they're approaching the search from multiple directions simultaneously, because nobody knows which direction the breakthrough will come from. Let's start with the most famous tool in the search, the Large Hadron Collider at CERN. The LHC is the largest and most complex machine humanity has ever built. It's a circular tunnel 27 kilometers in circumference, buried about 100 meters beneath the Swiss-French border near Geneva. Inside this tunnel, two beams of protons travel in opposite directions at 99.9999991% of the speed of light. When the beams are steered into each other, protons collide with a combined energy of 13 trillion electron volts. That's 13 tera electron volts, or 13 TeV. For a brief instant, the energy concentrated at the collision point recreates conditions that existed less than a trillionth of a second after the Big Bang. These collisions produce showers of particles that are captured by enormous detectors surrounding the collision points. The two largest detectors, ATLAS and CMS, are engineering marvels in their own right. ATLAS is 46 meters long, 25 meters in diameter, and weighs about 7,000 tons. It contains millions of individual sensor elements that track the paths, energies, and identities of particles produced in each collision. CMS is slightly smaller, but heavier at about 14,000 tons, built around one of the most powerful superconducting magnets ever constructed. These detectors record hundreds of millions of collisions per second, generating a flood of data that requires a worldwide network of computers to process and analyze. The LHC's greatest triumph so far has been the discovery of the Higgs boson in 2012. That discovery completed the standard models particle zoo and confirmed the mechanism that gives particles their mass. But the LHC was built for more than just finding the Higgs. It was built to search for new physics, new particles, new forces, new phenomena that could explain the mysteries the standard model leaves open. So far, that search has produced a frustrating result. Nothing unexpected has been found. No new particles beyond the standard model have appeared. No dramatic deviations from standard model predictions have emerged from the collision data. The LHC has confirmed the standard model over and over again with ever-increasing precision, but it hasn't found what lies beyond it. This doesn't mean the search has failed. The LHC is currently undergoing upgrades to become the High Luminosity LHC, which will increase the number of collisions by a factor of 5 to 10 starting around 2029. More collisions means more data, which means greater sensitivity to rare processes and subtle deviations from standard model predictions. New particles that are too rare or too subtle to show up in current data might reveal themselves with the increased statistics. The High Luminosity LHC will operate until at least the late 2030s, collecting a dataset roughly 20 times larger than what exists today. Beyond the LHC, there are proposals for even more powerful colliders. The Future Circular Collider, or FCC, proposed by CERN, would be a new tunnel about 91 kilometers in circumference, more than 3 times the size of the LHC. In its first phase, it would collide electrons and positrons with extraordinary precision, serving as a Higgs factory that produces millions of Higgs bosons and measures their properties with unprecedented accuracy. Any deviation from standard model predictions in Higgs boson behavior could point toward new physics. In a later phase, the same tunnel will be used for proton-proton collisions at energies up to 100 TeV, about 7 times higher than the current LHC. At these energies, physicists could potentially produce particles far too heavy to create at the LHC. China has proposed a similar project called the Circular Electron Positron Collider, or CEPC, which would also serve as a Higgs factory before potentially being upgraded to higher energies. Japan has proposed the International Linear Collider, a straight-line electron-positron collider that would complement circular colliders by providing different types of precision measurements. These projects are expensive. The FCC alone is estimated to cost around 20 billion euros over its full lifetime. Whether any of them will actually be built depends on funding decisions that haven't been made yet. But the scientific case is strong. If new physics exists at energy scales within reach of these machines, these colliders could find it. And even if new particles are too heavy to produce directly, precision measurements of known particles, especially the Higgs boson, could reveal the indirect influence of new physics through quantum effects. But colliders aren't the only way to search for new physics. In fact, some of the most promising searches are happening deep underground, in experiments designed to detect dark matter directly. The idea behind direct dark matter detection is conceptually simple, even if the execution is extraordinarily difficult. If the Milky Way is surrounded by a halo of dark matter particles, and if those particles occasionally interact with ordinary matter through some force beyond gravity, even extremely weakly, then a sufficiently sensitive detector should be able to catch one of these rare interactions. The current generation of direct detection experiments uses enormous tanks of ultra-pure liquid xenon buried deep underground. The xenon serves as both the target and the detector. If a dark matter particle collides with a xenon atom, the collision produces a tiny flash of light and a small number of electrons. Sensitive photomultiplier tubes lining the tank can detect both the light flash and the electrons, allowing physicists to determine the energy and location of the collision. The reason these experiments are underground, often more than a kilometer below the surface, is to shield them from cosmic rays. High-energy particles from space constantly bombard Earth's surface and would overwhelm the detector with false signals. Deep underground, the rock above absorbs most cosmic rays, creating a quiet environment where the faint whisper of a dark matter interaction might be heard. The Elok-Zeppelin experiment, or LZ, located nearly a mile underground in the Sanford Underground Research Facility in South Dakota, uses 10 tons of liquid xenon. It's currently one of the most sensitive dark matter detectors ever built. The Xenonity experiment at the Gran Sasso National Laboratory in Italy, buried beneath nearly a mile of rock in the Apennine Mountains, uses a similar amount of xenon. The Panda X experiment in China's Jinping Underground Laboratory, located beneath more than 2 kilometers of rock, the deepest underground laboratory in the world, is another major player. These experiments have been running for years and have progressively improved their sensitivity. They haven't detected dark matter yet, but each new generation of detectors sets tighter limits on how strongly dark matter can interact with ordinary matter, narrowing the range of possibilities. If dark matter interacts through any force other than gravity, we're getting closer and closer to the sensitivity needed to detect it. Future experiments with even larger detectors, potentially using hundreds of tons of xenon, are being planned. There's also the possibility that dark matter doesn't interact through any force except gravity. If that's the case, direct detection experiments will never find it. We'll need completely different approaches. Gravitational wave detectors, for instance, might be able to detect dark matter through its gravitational effects. Future space-based gravitational wave observatories like LISA, planned for launch in the 2030s, could potentially detect dark matter structures through the gravitational waves they produce, or the gravitational effects they have on other objects. Another frontier in the search for new physics is neutrino research. We already know neutrinos have mass, which is physics beyond the standard model. But there's much more to learn. The Deep Underground Neutrino Experiment, or DUNE, is currently under construction. It consists of a powerful neutrino beam generated at Fermilab near Chicago, aimed at enormous detectors located 1,300 kilometers away in the Sanford Underground Research Facility in South Dakota. The detectors will contain 70,000 tons of liquid argon, cooled to minus 186 degrees Celsius. DUNE is designed to answer several critical questions. It will make the most precise measurements ever of how neutrinos oscillate between flavors over long distances. It will determine the ordering of neutrino masses, specifically whether the third neutrino mass state is heavier or lighter than the other two. This is called the neutrino mass hierarchy, and knowing it is crucial for understanding how neutrino masses fit into the broader framework of physics. Most importantly, DUNE will search for CP violation in the neutrino sector. Remember, CP violation is the asymmetry between matter and antimatter. The standard model contains some CP violation, but not enough to explain why the universe is made of matter. If neutrinos exhibit significant CP violation beyond standard model predictions, it could point toward the mechanism that produced the matter-antimatter asymmetry in the early universe. This would be a major clue about one of the deepest mysteries in cosmology. The Hyper-Kamiokande experiment in Japan, a massive water-based neutrino detector containing 260,000 tons of ultra-pure water, is pursuing similar goals from a different angle. Together, DUNE and Hyper-Kamiokande represent the next generation of neutrino physics, and their results over the coming decade could fundamentally change our understanding of the standard model's limitations. Now let's talk about the theoretical side. While experimentalists build detectors and colliders, theorists have been trying to figure out what the new physics might look like. They've proposed numerous frameworks that could extend or replace the standard model, each addressing different aspects of its incompleteness. It's important to understand that none of these theoretical proposals have been confirmed by experiment. Their ideas, hypotheses, mathematical frameworks that might describe reality but might also be completely wrong. Science requires both imagination and humility, and physicists hold these ideas with open hands, ready to discard them if the data says otherwise. Supersymmetry, often abbreviated as SUSY, has been one of the most popular extensions of the standard model for several decades. The core idea is elegant. For every particle in the standard model, supersymmetry predicts a heavier partner particle. Every fermion, every matter particle has a bosonic partner, and every boson has a fermionic partner. The electron would have a partner called the selectron. The photon would have a partner called the photino. The quarks would have squarks. The gluons would have gluinos. If supersymmetric particles exist, they would solve several problems at once. They would stabilize the Higgs boson mass, solving the hierarchy problem. The quantum corrections from supersymmetric partners would naturally cancel the problematic corrections from standard model particles. keeping the Higgs mass at the electroweak scale without fine-tuning. Additionally, the lightest supersymmetric particle in many versions of the theory would be stable, electrically neutral, and weakly interacting, making it an excellent candidate for dark matter. And with the additional particles, the strengths of the three standard model forces, when calculated at very high energies, converge to a single value more precisely than they do in the standard model alone, hinting at grand unification. Supersymmetry is mathematically beautiful and solves multiple problems simultaneously. But there's a significant issue. The LHC has searched extensively for supersymmetric particles and hasn't found any. The simplest versions of supersymmetry predicted that partner particles should have masses within reach of the LHC. They don't appear to be there. This doesn't rule out supersymmetry entirely, as the partner particles could be heavier than the LHC can produce, but it does mean the theory has lost some of its original appeal. The simplest, most elegant versions are increasingly disfavored by data. String theory takes a radically different approach. Instead of treating fundamental particles as point-like objects with no size, string theory proposes that they're actually tiny, vibrating strings of energy. Different vibration patterns of the string correspond to different particles, much like different vibration patterns of a guitar string produce different musical notes. String theory naturally incorporates gravity, which is a major achievement. The graviton, the hypothetical particle that would carry the gravitational force, emerges naturally as one of the vibration modes of the string. But string theory requires extra dimensions of space beyond the three we experience. Most versions of the theory require 10 or 11 total dimensions. The extra dimensions would be incredibly small, curled up at scales far below anything we can directly observe. The way these extra dimensions are shaped determines the physics we observe in our familiar three-dimensional space. The problem with string theory is that it's extraordinarily difficult to test. The energy scales at which stringy effects would become directly observable are far beyond anything achievable with current or foreseeable technology. The Planck energy, where quantum gravity effects become important, is about a quadrillion times higher than what the LHC can reach. Building a collider that could directly probe string theory would require a machine larger than the solar system. There are physicists who argue that string theory makes indirect predictions that could potentially be tested. Predictions about the behavior of black holes, about the structure of the cosmic microwave background, about the properties of certain quantum systems. But these predictions are generally not specific enough to definitively confirm or refute the theory. String theory remains a mathematically rich and intellectually compelling framework that might describe the fundamental structure of reality, but might also be a beautiful mathematical construct that has nothing to do with nature. There are other approaches to quantum gravity that take different paths. Loop quantum gravity, for instance, proposes that space itself is quantized, made up of tiny discrete units rather than being a smooth continuum. In this framework, space at the smallest scales has a granular, foam-like structure. Loop quantum gravity makes specific predictions about the behavior of space-time at the Planck scale, though testing these predictions is, like string theory, extraordinarily challenging. Beyond these grand theoretical frameworks, there are more targeted proposals designed to address specific problems. Models with extra dimensions accessible at lower energies could explain the hierarchy problem. Hidden sector models propose entire collections of particles that interact with standard model particles only through gravity or through very weak forces, potentially accounting for dark matter. Composite Higgs models suggest that the Higgs boson isn't truly fundamental, but is made of smaller constituents bound together by a new force, similar to how protons are made of quarks. Each of these ideas makes different predictions that can, in principle, be tested. The challenge is that the energy scales and interaction strengths involved might be beyond current experimental capabilities. Physics might be entering an era where the next layer of reality is just barely out of reach, tantalizingly close but not quite accessible with the tools we have. This raises a profound question. What if the new physics is at energy scale so high that we can never build machines powerful enough to reach them? What if the answers to the deepest questions about the universe are forever beyond our experimental grasp? This is a real possibility, and physicists take it seriously. But there are reasons for optimism. History shows that breakthroughs often come from unexpected directions. The discovery of the cosmic microwave background radiation, which revolutionized cosmology, came from two physicists at Bell Labs who were trying to eliminate noise from a radio antenna. The discovery of pulsars came from a graduate student studying a completely different phenomenon. Gravitational waves were detected using technology that didn't exist when they were first predicted. There's also the possibility that new physics could show up in precision measurements rather than at high energies. This is the philosophy behind experiments like the muon G-2 measurement. You don't need to produce a new particle directly if it's too heavy for your collider. Instead, you can detect its existence indirectly through the subtle quantum effects it has on particles you can study. Virtual particles contribute to measurable quantities even if they're too heavy to produce as real particles. By measuring known quantities with extreme precision, you can infer the existence of unknown particles without ever seeing them directly. Gravitational wave astronomy represents another entirely new window on the universe. Since the first detection of gravitational waves by LIGO in 2015, this field has exploded. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. When two black holes spiral into each other and merge, or when two neutron stars collide, they send gravitational waves propagating through the universe at the speed of light. These waves carry information about the most extreme environments in the cosmos, environments where both quantum mechanics and gravity are important. Future gravitational wave observatories, both ground-based like the Einstein telescope planned for Europe and the Cosmic Explorer proposed for the United States, and space-based like LISA, will be sensitive to a much wider range of gravitational wave frequencies. They could detect signatures of phase transitions in the early universe, echoes from the structure of space-time near black holes, or even remnants of the Big Bang itself. Any of these observations could reveal physics beyond the standard model. Cosmological observations provide yet another path. The universe itself is a laboratory, and the conditions in the early universe were far more extreme than anything we can recreate on Earth. By studying the cosmic microwave background with ever greater precision, by mapping the distribution of galaxies across the cosmos, By observing the behavior of the universe's expansion over time, cosmologists can constrain and test theories of new physics. The Vera C. Rubin Observatory in Chile, expected to begin full operations in the mid-2020s, will survey the entire visible sky repeatedly over 10 years, creating the most detailed map of the universe ever made. It will track billions of galaxies and measure how their light is distorted by dark matter along the line of sight. This data will provide the most precise measurements of dark energy's behavior over cosmic history, and could reveal whether dark energy is truly constant or whether it changes over time. If dark energy varies, it would rule out the simplest theoretical explanation, a cosmological constant, and point toward more exotic physics. The European Space Agency's Euclid mission, launched in 2023, is mapping the geometry of the universe with unprecedented precision, specifically to understand dark energy and dark matter. These cosmological surveys complement the particle physics experiments, attacking the same mysteries from a completely different angle. Let me step back now and think about what all of this means. The Standard Model is one of the greatest achievements of the human mind. It describes the fundamental building blocks of reality and their interactions with a precision that borders on the miraculous. It predicted the existence of particles before they were discovered. It correctly calculates the outcomes of experiments with an accuracy that no other scientific theory can match. It's beautiful, powerful, and profoundly successful, and yet it's almost certainly not the final answer. It can't explain most of the universe. It can't incorporate gravity. It has cracks and gaps and missing pieces that point firmly towards something deeper. The Standard Model is likely what physicists call an effective field theory, a theory that accurately describes physics at certain energy scales, but breaks down at higher energies where new phenomena become important. We discussed earlier how Newton's mechanics turned out to be a brilliant approximation that was eventually contained within Einstein's deeper theory. The Standard Model is almost certainly in the same position. Whatever replaces it won't contradict it. It will contain it. The Standard Model's predictions will remain valid in the energy range where they've been tested. But the new theory will extend beyond the Standard Model's boundaries, explaining dark matter, dark energy, the matter-antimatter asymmetry, and the quantum nature of gravity, phenomena that the Standard Model, for all its brilliance, simply cannot reach. The cracks in the Standard Model, the anomalies, the missing pieces, the theoretical inconsistencies, these aren't signs of failure. They're the most valuable clues we have. Every great advance in physics has been preceded by observations that didn't fit the existing framework. The anomaly in Mercury's orbit that didn't match Newton's predictions led to Einstein's general relativity. The ultraviolet catastrophe in blackbody radiation that classical physics couldn't explain led to quantum mechanics. The strange behavior of light in the Michelson-Morley experiment led to special relativity. Today's cracks in the Standard Model could be tomorrow's doorway to a revolution in physics. The muon that wobbles slightly more than it should. The neutrinos that have mass when the theory says they shouldn't. The dark matter that holds galaxies together but can't be found in any equation of the Standard Model. The dark energy that pushes the universe apart for reasons nobody understands. Each of these is a thread that, if pulled, might unravel the next layer of reality. We live in a remarkable time. We have a theory that explains the fundamental structure of matter with extraordinary precision, and we know it's incomplete. We have experiments running and being built that could discover what comes next at any moment. The next breakthrough could come from a collision at the Large Hadron Collider, from a faint signal in a dark matter detector buried deep underground, from a neutrino oscillating in a way nobody expected, or from a pattern in the cosmic microwave background that doesn't match our models. It could come from a theoretical insight, a moment of mathematical clarity that suddenly makes sense of everything. Or it could come from something nobody has thought of yet, a completely unexpected observation that forces us to rethink everything. That's the beauty and the frustration of being at the frontier of knowledge. We know enough to know that we don't know everything. We can see the cracks in our best theory and recognize them as signposts towards something deeper. But we can't yet read what the signposts say. The standard model is not the end of physics. It's a milestone on a much longer journey. A journey that began when the first humans looked up at the stars and wondered what they were made of. A journey that passed through alchemy and chemistry, through classical mechanics and electromagnetism, through quantum mechanics and relativity. A journey that arrived at the standard model, the most precise description of nature ever achieved. And a journey that continues now, driven by the cracks and gaps and anomalies that tell us the story isn't finished. We don't know what the next chapter of physics will look like. We don't know if it will come in 5 years or 50 or 500. We don't know if it will be a single grand unified theory or a patchwork of discoveries that slowly fill in the gaps. But we know the cracks are real. We know the standard model is incomplete. And we know that somewhere in those cracks, in the space between what we know and what we don't, lies a deeper truth about the nature of reality. The universe has been extraordinarily generous with clues. Dark matter holding galaxies together, dark energy pushing the cosmos apart, neutrinos changing flavor as they travel through space, moons wobbling in ways we can't explain. The universe is practically shouting at us that there's more to discover. All we have to do is listen carefully enough, build sensitive enough instruments, ask the right questions, and have the courage to follow the evidence wherever it leads, even if it takes us to places we never expected. The crack in the standard model isn't a flaw, it's an invitation. An invitation to go deeper, to look harder, to think more creatively about the nature of reality. And if the history of physics is any guide, what we find on the other side of that crack will be more beautiful, more surprising, and more profound than anything we can currently imagine. The standard model describes the fundamental ingredients of reality with breathtaking precision. And it's not the final answer. There's something deeper waiting to be discovered. Something that explains the dark matter, the dark energy, the neutrino masses, the matter-antimatter asymmetry, and the quantum nature of gravity. Something that unifies all the forces and all the particles into a single coherent framework. We haven't found it yet, but we're looking. With the largest machines ever built, with detectors buried miles underground, with telescopes scanning the farthest reaches of the cosmos, with mathematical frameworks of extraordinary beauty and complexity, we're looking. And the cracks in the standard model are showing us exactly where to look. That's the story of where physics stands today. At the edge of the known, peering into the unknown, guided by the cracks in our best theory. Humbling, because the universe is so much stranger than we imagined. Thrilling, because the greatest discoveries might still lie ahead. Thank you for joining me on this journey tonight through the deepest questions in physics. And the next time someone tells you that physics is finished, that we've figured everything out, you can smile and tell them about the cracks that tell us the best is yet to come. Sleep well tonight, knowing that the universe still has secrets, and that somewhere out there, in a detector underground or a collider beneath the Swiss countryside, or a telescope pointed at the edge of the observable universe, the next clue is waiting to be found. Good night.